Okay, today we're going to take a look at antiderivatives and slope fields. Slope fields give us a way to visualize what an antiderivative might look like. And by the way, here's Dewey when he was about 3 or 4 months old. Okay, so we've seen this before, that if we take the derivative of a function, so if we take the derivative of x squared plus 3, we get 2x, or if we took the derivative of x squared minus 5, we'd get 2x. So they both produce the same derivative, which means if we're going backwards, taking the antiderivative, without given any more information, we have to have a plus c. So if we're given y prime equals 2x, we want to find y, then y equals x squared plus c, because there's potentially some constant there. If we have some more information, then we might be able to figure out what that value of c actually is. Okay, so if we're told that y prime equals 2x, and we're given an x and a y pair, and then we want to find the equation of y, well, we take the antiderivative, x squared plus c. We know x is 1 and y is 4, which means c equals 3. So the original equation would have been y equals x squared plus 3. This is called an initial value problem, because we're given the derivative, y prime, and we're also given initial values, x equals 1 and y equals 4, which allow us to find that constant. Anytime you're given an equation that contains a derivative, we refer to that as a differential equation. And initial value problems and differential equations can be illustrated with something that we call a slope field. A slope field is like a graph of the derivatives. So we can take any x, y pairs, and we can find the slope. We can find the derivative at that point. So when x is 0 and y is 0, the slope is 0. When x is 0 and y is 1, the slope is still 0. And for any point where x is 0, the slope is 0. Now if x is 1 and y is 0, the slope would be 2. So we can put a little line segment with a slope of 2. And anywhere where x is 1, we get a slope of 2. If x is 2, the slope would be 4, negative 1, negative 2, and if x is negative 2, the slope is negative 4. So if we know an initial condition, so say we knew that x was 1 and y was negative 2, we can plot that point. And using these little line segments here, we can let them guide us. Those line segments represent the derivative. The derivative is the slope of the original function. So what we're trying to do here is sketch a rough graph of what the function y would look like using the slope field and that initial condition. So we just kind of roughly follow those little line segments there, letting those guide us as the slope, and we can see that the antiderivative of y prime equals 2x would give us something that looks like a parabola, which we know is true. We know that antiderivative is x squared plus c, which is what allows this parabola to go anywhere up or down. And the rule of thumb to keep in mind is just don't cross the slope field lines. So if you use those as a guide, as long as your curve doesn't cross through any of those little line segments, you're probably going to be okay. Now you can see where the slope field comes in handy for something that's much more complicated like this. dy dx equals negative 2xy over 1 plus x squared. We have no idea how to find this antiderivative. We don't know how to find that original curve. But we can still get an idea of what it looks like by using the slope field. And since this one's so complicated, let's go ahead and just use the calculator to do this. Okay, so we can go to Menu, Graph Entry, Differential Equations, because we have an equation that's given in the form of a derivative. So y sub 1 prime equals, and we can type in our equation. Notice whenever we have y, we refer to that as y1 because it's referring back to the y on the left side there. And it gives us this. This has produced the graph of a slope field. So looking at this slope field right here, if you were to choose some point on there, you can visualize by taking a smooth curve following those slopes what that curve would look like. Okay, referring back to what we learned last chapter, integral from 1 to 4 of x squared dx, we call that a definite integral because when we take that antiderivative and evaluate, we get a definite value for the answer. We get some sort of a number. Now we could put the plus c in there, but it turns out it's not necessary because that c always ends up canceling out. So we don't bother putting the plus c when we take a definite integral because we know it's always going to go away. Now, if we leave off the limits of integration, integral of x squared dx, we call that an indefinite integral. We're not going to get a numerical answer here, we're going to get a function. We're going to find the antiderivative. So if we take the integral of x squared dx, that's just 1/3 x cubed plus c. So for an indefinite integral, we always have to include the plus c because we're finding the function that this came from, and that function could include some constant. Okay, many of these integral formulas that we're going to use initially are just our derivatives in reverse. And if you look in your quiz packet, these are all listed. So it gives us the next 15 or so numbers in our quiz packet, but the good news for us is it's everything that we already know. It's all of our derivatives just going backwards. And if we have something that's a little bit more complicated than we know how to deal with, we can try using our calculator. We can take the integral. Notice that we're choosing the option here that leaves off the limits of integration because we're taking an indefinite integral instead of a definite integral. And the indefinite integral just gives us the antiderivative. So we plug in x times sine of x, and that gives us sine of x minus x cosine of x. And notice that the calculator doesn't include the plus c, so we need to know that that plus c should be there.